Hi everyone, welcome to OneClass livestream. This is Chang, C-H-A-N-G. Today we're going to talk about some of the common math problems asked. So let's get started. Alright, so let's move on to our first problem. Our first problem is asking us how many sides does a dodecagon have? Okay, so first let's see Dodecagon is a special kind of a type of polygon, and a dodeca means 12 in Greek, so that means 12 in Greek. And a dodecagon is just very straightforward. It's a type of polygon that have 12 sides. So it's just a polygon that have 12 sides. So for example, this is 1, 2, 3. I guess I'll draw it bigger because it will be really hard to draw. Let's do this. Okay. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be a dodecagon. It's not really regular because, again, I was just drawing the dodecagon to kind of explain the idea to you. But basically, a dodecagon is just a special kind of polygon that have 6 sides, and that's what a dodecagon have. Some other example of polygons, for example, a type of polygon that you probably have heard of is a pentagon. So pentagon, penta just means 5, similar to how dodeca means 12. Penta means 5, and pentagon is just a polygon that has 5 sides. So for example, 1, 2, 3, 4, 5, this would just be a pentagon. You might have heard of the word Pentagon a lot. This is because in the United States, there's a building that's called Pentagon, and it's like a security building, and that is quite famous. So that's where you probably have heard of the word Pentagon outside of the math world. So yeah, a dodecagon is just a polygon that has 6 sides. Quite straightforward. Okay, let's look at a sample solution. Yes, it's a really brief explanation, but it is correct. So let's just say the solution is correct. And let's move on to our next problem over here. Cool. It is loading. All right. So our next problem over here is asking us what is the square root of 27. So let's write our question number. Question number 2. It's asking us what is the square root of 37. So in order to find the square root of 37, what people usually do is they try to use something called a prime factorization. However, 37 is already a prime number, so prime factorization wouldn't really help us too much over here. So usually there are two main ways that people solve this problem. The first way is the 3 main ways. The first way is just that this is the square root of 27, it's just root 37. So they'll just say something like, let's write solution number 1. Solution number 1. Solution number 1. People would just write the square root of 37 is root 37. Okay, this is one of the solutions that people gave, but this solution is kind of lame because you're just adding a square root sign to it, but it is a correct solution. There are some other solutions. For example, some people would just use a calculator, and they would just try to find the exact value, the exact decimal value of the square root of 37. So let us try that over here. The square root of 37. Yes, they'll just say the square root of 37 is approximately 6.083 or something like that. the curly equal sign just means approximately equal to versus exactly equal to. Okay, and a third way is to approximate the square root of 20 or the square root of 37. So we know that the square root of 36 is a perfect square, and the square root of 36 is 6. We also know that the next perfect square is that it's 49. So like the square root of 49 is 7. We also know that the square root of 37 is between the square root of 36 and the square root of 39. Or the square root of 37 is between the square root of 36 and the square root of 49, because 37 is larger than 36 and smaller than 49. So we can just approximate the square root of 36, saying that is approximately equals to 6 in bit, because the 37 is much closer to 36 compared to 49. There's another way that we could do it, and that is to use something called a long division. So we can try to use 37 to divide by 6, because 6 is really close. Because 37 is really close to 36, and the square root of 37 is really close to 6. So we can try to find the square root of 37, or try to approximate the square root of 37 using long division. So I guess we can try to do that, although we can also just get the answer from calculator really easily. So let's try that. 6 times 6 equals to 36, and we subtract these two numbers, and the remainder is 10. We put a dot here, and we drop the 0, and we put another dot here, and we know 1 times 6 is 6, and that's the best we can do for a number that's smaller than 10. And again, the remainder is 4, and let's drop another 0 here, and we know the largest multiple of 6, that's smaller than 40 is 6. So 6 times 6 equals 36, and the remainder is 40. So this just kind of goes 666 forever, because we're just repeating our calculation from this point on. So from here, we know that the square root of 36, or the square root of 36 is really close to the square root of 37, and the square root of 37 is approximately 6.16 to the infinity. But this is, again, just an approximation, and it's probably the best approximation you can do without resolving to using a calculator. So yeah, these are the 3 main ways to solve the problem of the square root of 37. Cool. Now let's look at our sample solution over here on the left side and see what they used. The SS, again, was the square root of 37, and we know that the square root of 37 is equals to question mark. Again, they just use our solution number 3 here, trying to approximate the square root of 37. And what did they use? They also use long division, but they use something that's a little different. And their answer is 6.082, which is really close to our real answer, which is 6.083 over here. Oh yeah, and our solution is quite similar to theirs too, but it has more differences. Cool. So let's just say something like, good job, the solution is correct. Cool. Now let's move on to our third problem. Okay, our third problem is asking us what are the basic trigonometric identities. So our third problem here asks us about basic trig identities. Now this is actually quite a broad answer, because if they're just asking us what are the trig identities, it would be easier, because although there's like a lot of trig identities, But basic trig identities is kind of an odd question because, you know, we can have a lot of trig identities. And which ones of them are basic? I guess that kind of depends on your school level, whether you're like in high school or middle school, and that kind of like determines which trigonometric identities are basic for you, and also like your schooling system for which province you're in, or which state you're in, or even which country you're in. So yeah, it's actually a quite broad question. But I think the most basic trig identities are I think the most basic ones I guess we can start with the tan identities. So we know the tan of theta, or tan of x, is equals to the opposite, or I guess is equals to sine of theta over cos of theta. And the cotangent of x is equals to cos of x over sine of x, which is also equals to 1 over tan of x. So this is kind of the most basic trig identities. There are also other trig identities. For example, we have the trig identity of cosecant of x and secant of x. So cosecant of x is equals to 1 over sine of x, and the secant of x is equals to 1 over the cosine of x. These are another kind of trig identities that are quite common. And some other trig identities include the double angle formulae. Let's write another box over here. The double angle formulae. And there are three main ones. The first is the sine of 2x is equals to 2 sine of x, cosine of x. And there's also the cosine of 2x. So that basically helps you to solve, to use like sine of x and cos of x to find the sine of 2x. So like when the size of your angle is doubled, how do you like find that those kind of values using like existing using existing angles? Okay, so the cosine of x equals to cos squared x minus sine squared x, and it also equals to 2 sine squared x minus 1, or sorry, it's equals to 2 cos squared x minus 1, 2 cos squared x minus 1, and also equals to 1 minus 2 sine squared, 1 minus 2 sine squared x. Okay, it's really easy to mix the order of these two formula up, so you got to be really careful of that. But these three are kind of the most common formula of cos 2x. There's also an extra one that I probably should cover here. Let's erase the box. We have another one that's about tan x. So tan of 2x is equals to 2 tan of x over 1 minus tan squared x. These are kind of all the double angle formulae, or I guess double angle identities, because they're both referring to the same thing, but some people call them formulae and some people call them identities. So yeah, these are kind of the most common ones. There's also other ones about the sum and difference of the angle, sum and difference identities, and it basically helps you to solve the sine of two angles added together, and the cosine of two angles added together or subtracted together, and the tangent of two angles of different sizes added or subtracted together. These are called the sum and difference identities. I'm not going to write them out, but they're also really common angle identities. I think these are kind of the four categories that are kind of the most common, or I guess there's another category that are pretty common, and they're called the Pythagorean. I think Pythai is like A. Pythagoras. Pythagorean identities. I think there are two main ones, or there are three main ones actually. One's about cosine squared x plus sin squared x equals to 1. They're the most common one that you'll probably see. And they're called Pythagorean identities because you know the Pythagoras Theorem is a squared plus b squared equals c squared. And the Pythagorean identities are derived using the Pythagoras, or they can be derived using the Pythagoras Theorem, and they also have the squares in them. So it's kind of like suitable to name them Pythagorean identities. And the other two Pythagorean identities for trigonometry we have is 1 plus tan squared x equals secant squared x and cosecant squared x. The third one this one you're probably not going to see as often, but the first two one are kind of what you'll see more often. So these are probably what you'll see more often. These are very useful, but I'm not sure you're going to see them until, I'm not sure if you're going to see them until like you're in later grade, like probably grade 11 or 12 in a Canadian school system. And these two are also kind of like more common. You're probably going to see them grade 10 or 11. Oopsie, the stars are not going with me. All right, but basically I was referring to sine 2x and cos 2x of double angle identities. But these ones, the tangent, you're going to see them everywhere. It's one of the most common ones that you're going to see. Cotangent, you're probably going to see it too. So it's cosecant and secant. They're all quite common. Okay, but the third one, right, let me just write it down as well. So it's about cosecant squared x. Cosecant squared x equals to, it's really weird. Whoopsie. Let me try to erase it. I'm just going to write it in another way so that it's, let's just write it in the way of 1 plus cotangent of x equals to cosecant of x squared. Whoopsie. So 1 plus cotangent of x squared equals to cosecant of x squared. That's kind of our third one of our Pythagorean identities. But again, it's not as common as the other ones. So yes, this is a common one. This is a common one. This is common. And this is probably the most common one you'll see, which is the tangent of x. Cool. So these are kind of like the more common identities, in my opinion. But again, there's like a lot of trigonometric identities. So depends on your schooling system, which of them are basic. It kind of depends on your school system and which kind of area of mathematics that you're going to cover. Now let's look at the sample solution over here. They separated them into the 4 categories. They have the cosine. Yes, I think we covered those as well. Did we? No, yes, we did. Kind of. I always wrote about secant and, or actually no, I wrote about all of them. I put the cotangent one here, and I wrote about secant and cosecant over here. Yes, the reciprocal identities. They basically wrote it in like the other way. So basically, we know that, for example, the cosine of x is equal to 1 over secant of x. And so the secant of x, if you multiply secant of x on both sides and divide cos of x on both sides, we would get to this formula written down over here. But then essentially, this formula is the same as the one that we're given. they also have the ratio identities, again, which we had over here. And they have the Pythagorean identities. Yep, they're the common one. I had it here as our last one. They also have the even and odd identities, or like the negative identities. They're actually you don't really need to memorize those. You might need to like memorize the other one, but this you don't need to memorize because you can just derive them or see them really quickly using the unit circle. So these are kind of like, or not using the unit circle. I guess you can also do it using the unit circle, but they're like they can be, you can just like see them using the unit circle or like using the graphs of cosine, sine, and tangent. So you don't need to memorize those over here. Okay, let's just see something like, good job, the solution is correct, the solution is correct. Cool, let's move on to our next problem. They didn't mention double angle identities or sum and difference identities. I presume they just don't think these are as basic as the other ones, but I think they appear quite often. But again, it depends on which schooling system you're in. Alright, that sounds our third problem about basic trigonometric identities. Let's check what other questions are asked. Okay. Oh, that's perfect. Okay, so the question here, the next question asked was, how do we simplify cos x plus y to trigonometric functions of x and y? We actually literally just covered it. Let's use another color of ink. Let's use blue here. So we actually just covered it, or I guess we didn't write it out, but we basically just covered it over here. Again, as I've said before, the sum and difference identities are actually seen quite common. So this is actually can be found using the sum and difference identities. I didn't write it out because that would be like a lot of things to write it out, but I guess now we have a opportunity to write this out. So let's go to our fourth problem. Our fourth problem, and it's asking us what is cos x plus y. This is essentially, I guess you can also derive it, but it's really hard. So the better way is probably just to memorize it. That would make your life much easier, and you probably wouldn't have enough time on tests to derive it. I guess you could derive it while doing the test, depending on how fast you derive things, but it would be much easier just to memorize it, honestly. Okay, so what's cos x plus y? Cos x plus y is actually equals to cos x, cos y, plus sin x, sin y, I think. Yes, I think it is. Or actually cos, yes, it's actually minus sin x, sin y. Again, while you're memorizing the sum and difference identities, you really need to pay attention. Let's do pay attention to the signs, because the signs are weird. Because for cos of x minus y, we have cos x cos y plus sin x sin y. But for cos of x plus y, we have cos x cos y minus sin x sin y. So the sign is different for cos. But when it comes to sine, or it comes to the function sine, the two signs are actually the same as the one in the brackets. So like, it's just something that you probably should pay extra attention to while you're doing the memorizing, because getting the question wrong just because like a plus or minus sign is kind of like, you know, it's not good, because you will be so close to your answers and then it's just a sign and then your answer is wrong. Okay, so this is how we would do the problem over here, and I'll just highlight our solution. Highlighter, I'll just highlight our solution in yellow. So here's our solution. Here's our solution. I guess this is not really highlighted because the highlighter wasn't big enough. But yeah, here's our solution. Cos x, or cos of x plus y, is just equals to cos x cos y minus sin x sin y, based on our sum and difference identities. So yeah, this is how we solve this problem. Now, let's look at the sample solution. Oh, our sample solution here is perfect, it's correct. They probably it probably would be easier if they just mentioned about the sum and difference identity, but that is fine. So let's just say that that's correct. Yay. Cool. Nice. Now let's move on to our next problem. Okay, our problem number 5. And what problem number 5 does is that it asks us what is the slope of a regression line. So I'm assuming they're talking about the regression line in the context of statistic. That would be the most logical answer. So the slope of a regression line. So the slope of regression line. First, let's talk about the response and explanatory variables. So for linear regression in statistics, you have the y's and you have the x, which is somewhat similar to the y's and x you see in calculus, but not exactly the same. So usually we use the y's as like the explanatory, or we have the y's in like a sample, or we also have the x in a sample, but we're trying to explain the relationship, or trying to visualize the relationship between the y's and the x's. So how we do that is that usually we would use something that's called a scatter plot. So there will be a lot of dots of different values of y's and x's. Over here, we just have a lot of random dots everywhere. What we're trying to do is we're trying to use the least square estimation. We're trying to, or the least square methods. Let's do the least square methods, or whoopsie, Control Shift. The least square method. We're trying to use this method to like fit those little scattered dots, to fit these data points into a line where we minimizes the distance between the square dots to the line that we're going to fit. So that way we can basically find a line that fits the data the best, or that best kind of gives the information of the data. So let's just try to draw a line over here. Usually you will just do it as like a software, because it's kind of hard to just eyeball it, or it's not going to be as accurate if you eyeball it. Say this green line over here is our least square line, or it's our linear regression line, or least square line, depending on how you call it. So the slope of this regression line, which is just the slope of this green line. So again, you know, to find the slope, we just find a point. So this point is on the data, and we find another point on the data, or find another point on the line, and we're just trying to get the changing y and have the changing x, and trying to find their slope. So their slope, again, just explains the amount of changing y for a certain amount of changing x. So it kind of like projects the changing y in terms of changing in, given that the amount of changing in x. So for example, if we have some new data points, over here, and we know the value of x of this data point, but we don't know the value of y of this data point, and want to try to find the value of y on this data point, so y question mark, we know x. And what we're going to do is that we're just going to try to use this regression line we found, and we're going to try to get the value of x on this regression line. See, here is like on the same line, because it's the same value of x, and x is here, and we're trying to get y. Let's just call it y1, and we'll try, and we know the value of y1 on this regression line because we know the slope and we have the equation of the line. So here we're just going to estimate the value of y over here, which is unknown, using the value of y of this line. So yeah, the slope of the regression line has a lot of uses, and linear regression also have like a lot of uses. It's probably the same. It's probably one of the first few concepts that you're going to learn in statistics. So it is quite useful, and this is kind of what the slope of a regression line symbolizes. It basically just helps you. It basically just represents the changing y over changing x, and it can give you the changing y if the changing x is already known. Cool. Let's look at the sample or the sample solution. Yes, they had the same answer and what we explained here, and yes, they also gave some more background information. And yeah, again, this is kind of what we said. The relationship between the changing y based on x also predicts value of y given the x, and tests for like linear relationship. Okay, let's just say something like the solution is correct. Cool. Let's move on to next problem. Our next problem here asks us, how do we verify the trig identity cosecant x cos squared x plus sin x equals to cosecant of x? So this is actually a verification problem, and when someone asks you to verify something, you actually start at the left side of the equation. So in this case, we'll start with cosecant of x cos squared x plus sin x, and we're trying to simplify the left side of the equation to try to get this side of the equation to equal to the right side of the equation. So we're basically trying to get this side of the equation to equal to cosecant of x in the end. And this is how we verify this identity. Of course, if you want, you could start at the right-hand side and try to get to the left-hand side, but it's much more difficult, in my opinion, to do it the other way around. At least, or in this case, it is. But maybe if this question is written as verifying cosecant of x equals to cosecant of x cos squared x plus sin x, in that case, verifying it the other way around is much easier. So you can like have a scrap paper and then just do some like rough calculations of verifying the other way around, and then try to write down the proper answer, going like from the bottom step to the top step, so going the other way around. That would also work. All right. So yeah, let's just try to verify this. So we're basically just trying to simplify this. So in this case, we know sin of x is pretty much as simple as it gets. We probably don't need to do something with sin x just yet. And cos squared x, again, I can't really see how we would do something about it. But cosecant of x, we can do something about that. So again, just based on the identity we talked about before, we know that, let's write down another color. We know that over sin of x, so we know this can be simplified. So now let's just try to write the cosecant of x as 1 over sin of x in the equation. So now we have cosecant of x equals to 1 over sin of x cos squared of x plus sin x. So next, let's just move cos squared x on top of the sin x. So we have the same equation as the following. Now we have a fraction and we have a fraction which is cos squared of x over sin x, and we have another sin x over here. So let's just try to get the fractions to have a common denominator, and then we could probably finish our simplification. So we know that cos squared x over sin x is we're just writing it down as the same thing as the same term as what we had in the previous step. But in order for sin x to have a denominator of sin x, we need to multiply the sin x term by 1, and we need to write this 1 in a special form. We can write this 1 using sin x over sin x. This way, the value of sin x hasn't changed, and also we know that sin x over sin x is just 1 because a term over itself is equals to 1, or I guess a number over itself is equal to 1. So yeah, let's just do this here. So we have sin x times sin x over sin x. That would be just multiply the sin x by the top or by the numerator of the fraction, and we have sin squared x over sin x over here. Now, the two fractions in our expression has the same denominator, so we can just add the numerator together. So now we have cos squared x plus sin squared x over sin x as our next step. Now, we know that one of the Pythagorean identities is 1 equals to cos squared x plus sin squared x. So we know that cos squared x plus sin squared x is also equal to 1. And then for the next step, we can just interchange the 1 with the cos squared x plus sin squared x because they have the same value. So the result of our equation wouldn't change. So yeah, we know that cos squared x plus sin squared x collectively over sin x is equals to 1 over sin x. Again, for our first step, we know that 1 over sin x is the same as cosecant of x. So we know here we just have cosecant of x. And we are done of verifying this identity because on the top we started with cosecant of x, cos squared x plus sin x, and we arrived at cosecant of x. So we started on the left hand side of the equation that we want to verify, and we ended on the right hand side. So we completed our verification, and this expression is true. Perfect. Now let's look at our sample solution over here. Yes, they use the same steps as we did. They didn't write out the steps in as much of the detail as we did, but that's just because I just thought explaining in more detail should help. So yes, that's pretty good. So let's just say the solution is correct. Good job. Yay. The solution is correct. Alright, now let's move on to our next problem. Our next problem here just asks us, how do we simplify sine of arctan of x? Okay, so our seventh problem here, let me just zoom in a little, zoom in, and our seventh problem here. Okay, our seventh problem here asks us to simplify sine of tan inverse of x. So first, I know some people like to use the notation of the inverse of tan of x, but I don't really like that notation. I like to use the notation of arctan of x, because the inverse of tan of x, some people just confuses it with cotangent, which is the reciprocal of tan x. So like this is kind of a confusing notation. So I prefer just to use arctangent of x. Alright, so we know that this, alright, actually let's put this thing in blue so that you're not confusing it with our steps, because this is kind of like a side note or like some pre-existing things that we already know. So we know sine of inverse tan of x is basically just saying sine of arctangent of x. So important thing, or I guess I should start by saying that there are two main ways to solve this problem. Two main two main ways to solve this problem. I prefer one of them, and the one that I'm going to show you is probably the easiest or the more intuitive way of the two. Let me just briefly state the two possible ways. The first way is to use a lot of trig identities. So a lot of trig identities. Which specific trig identities you're going to use will depend on the specific question. But to me, it's just kind of like confusing and not as intuitive as like the other way of solving this problem, because you need to memorize all of trig identities and you need to get your head really clear about those trig identities and what they mean, which is just not as easy as the other problem. The second problem is just like drawing the triangles. I think it probably has a fancy name, but I just like to call it drawing the triangles because I don't know, it just sounds more straightforward to me, and this is actually like a really straightforward ways of solving this problem. Alright, so I'm going to solve the problem using the second way or the way that's more straightforward. Okay, so before solving this problem, I just want to give you a note. So like, note. So we know that the arctangent of x is the inverse of the tangent of x. And we also know that sine of x, cos of x, and tangent of x, they take in an angle and they outputs a value. So the inverse of the sine of x, or the inverse of sine, cosine, and tangent, they are the inverse, or they are the opposite, or they like they are like the output of the sine cosine, and tangent of x is the input of arcsine, and arctangent of x. So we also know that sine of x, kind of the input is an angle and the output is a value or a number. Similarly, the tangent of x, the input, or the arctangent, so like arctangent of x, the input is the value that the tangent of x outputs if the x is the same, and the output is the angle. So we know the arctangent here, or arctangent of x, is actually equals to an angle, which means that sine of arctangent of x is actually sine of an angle. So let me just say sine of arctangent of x is equals to a sine of an angle of theta here. So yeah, I just kind of want to get this really clear in your head, because some people, they just, or I guess a lot of students, they just look at this expression and this expression just kind of scares them a lot, because they're like, oh, how come like a tangent is instead of a sine, because that doesn't quite make sense. Well, the answer is just because the tangent, or this is not just the tangent of x, but it's the arctangent of x. So it's the inverse of x, and it's what tangent of x outputs. So the tan of -1 of x, let's just write down here. The tan of -1 of x, or the arctangent of x, or the inverse tan of x, it's an angle. Sometimes teachers or instructors, they purposefully write it this way to confuse you. And yeah, don't be confused, it's just an angle. Alright, now let's move on to our process of drawing a triangle. So you can just draw a random triangle, anyways you like. As long as it's a right angle triangle, then it's fine. So yeah, just draw a right angle triangle. And from here, we know that our arctangent of x is equals to an angle. So let's just write an angle here and pretend that the angle is the arctangent. Also, we know that the arctangent of x is an angle, and we know that the tan of this angle is or actually we don't know, but we know that trying to find the arctan of x. So, and again, we know that the arctan of x is equals to this angle. Right over here, I'm just rewriting it again. So the tangent of the angle, tangent of the same angle is equals to x. As I've said before, the tangent of an angle is equal to x. X is a value, and the arctangent of x is the inverse of the tangent, or the arctangent function is the inverse of the tangent. So the arctangent function basically eats what the tangent of x outputs and gives what the tangent function input. Okay, so now we know the tangent of the same angle is equals to x. So the tangent of the same angle is equals to x. We also know that tangent is equals to opposite over hypotenuse. And we know that the function x is also equal, it has the same value of x equals x divided by 1, because x is just the same as x over 1, because any number over 1 is that same number. Okay, so we have x is equals to x over 1, which also means that the opposite can be x. So we have opposite equals to x, and hypotenuse is equals to, oh, I'm really sorry, tangent is actually opposite over adjacent. The formula, oopsie, the eraser doesn't quite work. Oh, is that a problem with OneNote again? Maybe I should just switch to another software, because OneNote has so many problems. Okay, tangent is actually not opposite over hypotenuse. Tangent is opposite over adjacent. So let me just write adjacent over here. Okay, so tangent is opposite over adjacent. So the opposite here will be x, and the adjacent here would be 1, which also means that the opposite of this angle is x, as we talked about over here. So x is over here, and the adjacent of this angle is 1, so 1 is over here. As we noted previously, this angle is a right-angled triangle. So based on the Pythagorean Theorem, states that a squared plus b squared square root equals c, where a and b are two sides of the triangle, and c is the hypotenuse of the triangle. So here we have a squared as a x squared, b squared as a r1 squared, and we have a squared plus b squared equals to the hypotenuse of the angle. So now we had both our a squared and b squared, and we know our hypotenuse is x squared plus 1, or the square root of x squared plus 1. So now we filled all the information of our triangle. Next, so what our next step is? We already know that, so we wanted, let me just remind you that we wanted to find the sine of the arctan of x, and we also know that arctan of x is theta, so we want to find the sine of theta, and the sine of theta is the same as the sine of this theta over here. So we know from the trig, our basic rules of trig, that sine of x okay. Oh, OneNote is not working. But our sine of x, yes, does it start working again? Perfect. It changes the color of everything, but I mean, it's working. So let me just change it back to black really quickly. Change the sign to black. And let me just continue with our solution. So we know as the sine of x is equals to opposite over hypotenuse. And let's move our final solution down below so that we kind of have like a more clear view. So we know that sine of x is equals to opposite over hypotenuse. And our triangle over here, the opposite of the angle equals to opposite over hypotenuse. And our angle here, the opposite of our angle is x. So the opposite is x. And the hypotenuse of the angle, the hypotenuse is the square root of x squared plus 1, x squared of x squared plus 1. So sine of theta, okay, let's write sine of theta up here. Okay, so we know that the sine of theta, or in other words, the sine of the arctangent of x is just equals to x over the square root of x squared plus 1, and that's our final answer. Okay, that is kind of a long solution, but I guarantee you that it's easier and more straightforward and makes much more sense compared to using a lot of trig identities. So let's just do a quick recap. So first, we know that the arctangent, or first we know that the arctangent of x, or the inverse tan of x is just the arctangent of x, which is actually an angle. And we know that the sine of, we're just trying to find the sine of an angle that is the arctangent of x. So we just want to find the sine of this angle, which is the arctangent of x. So based on the fact that the arctangent of x can also be expressed as the tangent of the theta, which is x over 1, so we can just fill in the blanks of the triangle with the x over here and the ones over here. Then we would want to find the hypotenuse of the triangle because we're trying to find sine ultimately, and sine is opposite over hypotenuse, so we need the hypotenuse. We use Pythagoras Theorem to find the hypotenuse of the triangle, which is just a squared plus b squared equals to c squared. So it should be quite straightforward, a simple calculation. Now we have the hypotenuse of the triangle, and we know that sine is opposite over hypotenuse. So we just find the opposite of this angle, which is x, and we know the hypotenuse of this angle is the square root of x squared plus 1. So we just do opposite over hypotenuse for our sine, which is x over the square root of x plus 1. And this is our final answer right over here. Excellent. Now, this concludes our problem of simplifying the expression sine of arctangent of x. Now, let's look at our sample solution on our left-hand side. They actually used the first way, which is using trig identities. It is quite long, but essentially, or at the end, they arrive at the same answer as us, which is x over the square root of 1 plus x squared. Nice, and these are the 3 trig identities that they used. Nice? Let's look at, so they have, or I guess we can briefly step through the answer. Arctangent of x is theta, right? X equals tan theta, perfect. Sine of theta equals tan theta over secant theta, because tan of x equals sin x over cos x, and secant theta is 1 over cos x. Cool. And they just interchange the x here with the tan up above. Alrighty, so let's just say correct solution. Good job. Good job. Okay, now let's move on to our next problem over here. Okay, our next problem over here just asks us what is 0.6225 as a fraction. So basically it's asking us to convert a decimal to a fraction. We know that 0.625, the smallest place of 0.265, the decimal, is the third place to the right of the dot. So it is the 1,000th place because it starts with the 10th place, the 100th place, and the 1,000th place. That's the smallest place. So what we do here is very simple. We just write our 1,000 as a denominator, and we put everything to the right-hand side of the dot over here on the numerator. So we have 625 over 1,000, and now we need to simplify, and we know that the greatest common factor of 625 and 1,000 is 125. You might not see that directly. If not, don't worry, that's fine. You can just do 5, that's the most straightforward one, and you do 5 again, and you do 5 again, and you're going to arrive at the same answer. Just make sure that after each step, you need to double check the greatest common factor of the numerator and the denominator, and make sure that their greatest common factor is 1, so that we don't need to further simplify the expression or the fraction. Cool. Now we just need to divide both the top and bottom by 125 by 125. 1000, the denominator divided by 125 is 8. 625 divided by 125 is 5, I believe. Let me double check. Yes, 2, 2, 1, it is 5. Perfect. So now we have our answer. 0.625 as a fraction is 5/8 or 5/8. Let's look at a sample solution here. Perfect, perfect. They used the same way as us, or at least a very similar way as us. So let's just say, great job, the solution is correct, or excellent solution. Cool. Now let's move on to our next problem. Over here. Nice. Oh, okay, our next problem is how secant of negative pi over 6. So secant, or I guess it's asking us for the exact value of negative pi over 6. Before starting our question, we need to know that the secant of an angle, or I guess the secant of an angle over the cosine of an angle. So in order to evaluate the secant of negative pi over 6, we need to find the cosine of negative pi over 6, and then we'll just reverse the order of it. So now let's try to find what's the cosine of negative pi over 6. So first, we need to know what is our reference angle, and our reference, let's just do the unit circle here. This is a unit circle, or I guess I'm not actually going to draw the actual circle, but instead of like just a set of coordinates. But I think the goal here is negative pi over 6. So let's just draw our negative pi over 6. If you're not as familiar with radians, I'll tell you what is negative pi over 6 in degrees. Over 6 in degrees is just, negative pi over 6 in degrees is just 30 degrees. So the line should drop. Whoopsie, that's huge. Our 30 degrees is probably around here, and this is just negative pi over 6. Negative pi over 6. Perfect. So our reference angle is 6, and over here, because it's on the right hand side of the y-axis, here it's actually positive. And in the circle, the x values have the same signs as the cosine values, so we know that our cosine is positive. Since secant is 1 over cosine, our secant is also positive. Next, in order to find the exact value of pi over 6, we just use our special triangles here. There are 2 of the special triangles, and this is just one of them. And for the 2 of the special triangles, the angle here is pi over 3, and the angle there is pi over 6. And we just need to find the secant of negative pi over 6, which in this case has the same value of the secant of pi over 6. And we know that secant is 1 over cos x, so it's 1 over the cos pi over 6. 1 over, our angle pi over 6 is over here, and cosine is adjacent, root 3, over hypotenuse, root 2. So our secant of negative pi over 6 is 2 over root 3. Perfect. Our solution over here, their sample solution is actually incorrect because the value is actually positive instead of negative. You might be a little confused about that. Where did they get 2? Let's just try over here. So basically, some people, they don't like having, not like some people, but it's kind of a international standard, but people in Canada don't, or at least are fine with this. But the international standard is that the radicals on the bottom should is technically not in its simplest form, but unless we simplify the radical at the bottom, which is times this fraction by 1, and we have the root 3 over here, so that we can cancel out the root 3 and move the, so on the numerator we have 2 times root 3, which is 2 root 3. In the denominator we have root 3 times root 3, which is 3. So here we don't have a radical on the bottom, but we have a radical on the top. But it's fine because the convention, or the international convention, is that as long as the radical is not on the bottom, it's considered simplified. Cool. So the value of their expression is correct, but the sign of their solution is not correct. You know what? I'm not that confident, so let me just solution is indeed correct. So we're asking negative pi over, or I think they only support degrees instead of radians, which is negative 30 degrees. It gives an error. What's the error? Oh, it doesn't even support secant. So let's just do 1 over cos of negative 30 degrees, and it's positive. Okay, so our solution is correct, and the sample solution is wrong. So let's just say the sample solution is wrong, the solution is incorrect. I don't need to capitalize it. That's what I mean to capitalize it. So let's say the solution is incorrect because positive instead of negative. So angle, or the reference angle, or let's just say the angle, is in the 4th quadrant. And by that, I just mean that for a unit circle over here, the quadrant actually starts counting. The quadrant starts counting from here. This is the 1st quadrant, this is the 2nd quadrant, this is the 3rd, the 4th quadrant. And our angle, our green line, which symbolizes our angle, is actually on the 4th quadrant, where x is cosine. So yeah, let's just say that. Okay, and let's just say the solution is incorrect. Now let's move on to our next problem. Problem number 10. Problem number 10. Oh, we're using a marker instead of pen. That's why it's so thick. Okay, let's switch back to a pen. Our 10th problem over here. 10. The 10th problem over here is asking us to convert to 2.5 into a fraction and a percentage. So we're converting our 2.5 into a fraction and a percentage. So first, let's do fractions. In order to convert 2.5 as a fraction, let's write 2.5 into 2 parts. 2 plus 0.5. And 2 is just an integer, so let's just write as 2. And 0.5 is actually, this is just the 10th place right over here, the 10th place, as the denominator, and put 5 as the numerator. So we have our 2.5. The decimal is the same as 2 plus 5. We need to check whether the decimal or the fraction is in its most simplified form. The answer is no. Why not? Because its common factor is larger than 1. The greatest common factor is actually 5 in this case. So we need to divide both the top number and the bottom number by 5, which gives us 5 over 5 is 1, 10 over 5 is 2. So we have our 2.5 as 2 plus 1 over 1 half, which is 2 and 1 half, which is also equals to 3 half if you want to get it in another form. Okay, so this is our 2.5 into fraction form. Now let's try to do it in the percentage form. Percentage form, percent. Percent. Okay, so we know that 1 is equals to 100% because the percent sign essentially it just means, let's write it in another color. So the percentage sign essentially just means over 100. That's just all that is to the percentage sign. It's just something that people invented to see, to read math numbers more clearly, and that's why the percentage sign was invented. Okay, so we know that 100 percentage sign is essentially 1 over 100, so we know that 1 is 100% because it is 100 times the percentage sign, which is 1 over 100, and it's 100 over 100, which is just 1. Alright? And how do we convert 2 to a percentage? So from the above, we know that 2 in fraction form is actually 3/2. So you want to convert the bottom number to 100. So what is 100 over 2? 100 over 2 is 50. So 2 times 50 is 100. What should you put on the top? 50 as well. Because if you put any number other than 50, then you're multiplying 3, which is going to change the value of 3/2. However, if you're multiplying the 3/2 by 50 over 50, 50 over 50 is just 1. You're not changing the value of 3/2 at all. Alright? So now at the numerator we have 3 times 50, which is 150. On the denominator we have 2 times 50, which is 100. Oh, I'm so sorry. Over here I have 2 and 1/2. I said it's equals to 3/2. Sorry, I lied. It's actually equals to 5/2. So we have 5/2 over here. And at the top we have 5 times 50, which is actually 2. And on the bottom we have 2 times 50, which is 100. So right now we have our fraction of 5/2, or a decimal of 2.5, is actually equals to 250 over 100, which, whoopsie, 250 times 1 over 100, as we talked about before, 1 over 100, it's like the percentage sign. It's the value of the percentage, 1 over 100 is the value of the percentage sign. So we just have 250 times 100, or 250 with the percentage. From here, that 2.5 is 250%. And that is our answer. Perfect. Now let's look at our sample solution over here. Our sample solution over here. Perfect. They just wrote it as 2 and or 5 over half, or 5 over 2. Nice. It's correct. The conversion is correct. Amazing job. Yeah. Nice. Let's see what's our next problem. Nice, we have another easy problem asked. Okay, so the problem here just asks us to find a polynomial function, or it asks us how do we find the polynomial function that has 0s, 0, 1, or 0, -2, and -3. Okay, so I'll tell you a little bit about polynomial functions. So polynomial function, let me not tell you about polynomial functions. I feel like that would, actually, I'll tell you about polynomial functions. So first we need to understand what are zeros. So the zeros of polynomial function basically means that when the function crosses the x-axis, this is a 0. And we know that the value of y is 0 because that's when a function crosses the x-axis. So we know these points, this point, over here, they are both zeros because when it crosses and touches the x-axis. In this case, we know that the x is something like maybe let's just say it's 5 because it is positive. And here we know that the x is probably something like -7 because it is negative over here. And again, the y value is just 0 because that's when the function crosses or touches the x-axis. Perfect. So in this case, we want the find the polynomial function that has 0, 0, -2, and -3. So from here, we know that this function actually has, how do you say it? This function here actually would be of the form x minus 5 times x. Or I guess that kind of, let me think about how to explain it. Okay, now let's look at a separate function. Let's just say there's a function of x that equals to x squared minus 1. And we just need to factor it. I'll just do it quickly for you. Once you factor it, that function would be x minus 1 and x plus 1. Now, let's just quickly draw this function. You to draw this function, we know that the function would look like this because if the x is positive, that means that it concave up. And we also know, and here, how do we find those two coordinates? We know that it would just be x equals to positive 1 or negative 1 because x minus 1 would equals to 0. That's when the function would equals to 0. And when x minus 1 equals to 0, we have x minus 1 equals 0, and 0 which is equals to the x of which is equals to 1. So x would equals to 0. And again, let's do the other one. When it's x plus 1 equals to 0, that's the other place that the function is going to equal to 0. And here we have the x value as -1 when the function is equals to 0. So yeah, this is the example that's different of how about the two x-intercepts of when the function intercepts the x-axis. Okay, so similarly, for our current question, how do we find a polynomial function that has those 3 zeros? All we gotta do is, let's just say our function for this solution is g of x. All we gotta do is that we need to find a function that has zeros -2 and -3. We know from here that when x is equals to -2, so when x is equals to -2, in order to find a 0, we need to plus 2 on the both sides, so we have x plus 2 equals 0. So we know one of the terms of our function is x plus 2. Similarly, when x equals to -3, we just need to plus 3 on both sides, so the other one function is equals to x plus 3. Now, our third 0 is just 0. How do you do that? It's actually very similar. So we know that we have x equals 0, and when x equals 0, we just need to put x here for our x equals to 0. So yeah, this is our polynomial function that we need to find. We have x plus 2 times x plus 3 times x. And this is our answer form. So we can just leave it like this. But we could also simplify our function even further. So let's just do that. In order to simplify it, we just need to times each term by the other. For those kind of questions, we would always have 4 terms. It would be the x times x, which is x squared. Next, x times 3, which is 3x. Next, 2 times x, which is 2x. And we have 2 times 3, which is, we just have these two functions multiplied together. And then we collect like terms. So we collect the 3x and the 2 plus 5x plus 6. And then we just have multiply the entire x, which will be x cubed plus 5x squared plus, and that is our function, our polynomial function that has the 0. And this would be our final solution over here. Perfect. Nice. Now let's see what is the sample solution. The sample solution here, yep, they gave a brief explanation. But they just give you the expression without really explaining it too much. I guess you can also do that. That would also be a way to do it. You just use the expression. But this explanation actually helps you to understand the why of why this expression exists and why you're using this expression to find a polynomial function. Cool? Okay, their solution is correct. It's the same as ours. Amazing. Amazing. Excellent solution. Excellent solution. And the solution is correct. Now let's move on to our problem number 12, which is straightforward problem. Write 0.260 into a fraction. Again, we go to, this case is the third one, and it's the 100,000th place of the decimal, and we just need to put the 1,000 as a denominator of a fraction, and we write everything to the right side of the dot on top as the numerator of a fraction. Next, we just simplify it. Again, their common factor is 125. That's the greatest common factor of the numerator and the denominator. I felt like we've done this question before in the earlier part of this video. Probably someone just like posted this this question twice, so it's like a duplicate, I think. Or maybe I remember wrong, but I think we've done this problem before. Okay, and 1,000 divided by 100 over 12, actually 8, because 1,000 over, and 675 over 125, it is 5. So our fraction, 675 as a fraction, is 5/8. That's why the sample solution over here. 725 is actually, oh, I see. What we have done is actually 0.625, and this is 0.675, which is a different problem, and 0.6 is actually not divisible by 125 because it's not a fraction. It's not a multiple of 6 of 125. So yeah, I mistakenly thought it's 625, but no, it's 675. Cool. So instead, the greatest common factor is actually 25, or we can do 5 and then do 5 again, but it's actually 25. So yeah, I actually recommend you, or probably me in the future, to do 5 and 5 again, because that way it's guaranteed that our solution is correct, versus to doing 25 directly, our solution might not be right. So 1,000 over 25 is 40, and 675 over 25, let me see, it is more than 20, is 20 plus 25 over 5, 20 plus 7, so it's actually 27. So yeah, our 0.675 converting into a fraction is actually 27, should be our answer. Alright, now let's see. Right, their solution is correct. So let's just say, great job. The solution is correct. The solution is correct. Perfect. Next problem. Cool. Our next problem asks us to find the value of arctan of negative root 7. So problem 13 here asks us to find the value of negative root 7. So in order to find the arctan of negative root 7, first we need to find our reference angle. So let's do a reference angle. We know that is the triangles, and in this case, we know the special triangle that has root 3 over here. So let's just draw that special triangle has root 3 as one of its sides. Okay? And let's put down the angles here. This angle is 60 degrees, or that angle is 30 degrees, or pi over. Next, we know that the tangent of a function, the tangent of an angle is opposite hypotenuse of the hypotenuse. So for which angle the opposite over hypotenuse is √3? We know I'm really sorry, the tangent of a function is actually the opposite over adjacent. Opposite over hypotenuse is sine function, the tangent function. Okay, the triangle to see which function has the opposite is of value √3. So we know the answer is actually the pi over 3, because we know that the tan of pi over equals √3. We know that the tan of pi over 3 is √3 over adjacent 1 equals to √3. So we know from here that tan of pi over √3. Next up, we know that our angle is not just pi over 3, because we know although the tangent of 3, meaning the arctangent of √3 is equals to pi over 3, tangent of negative √3, not just of x. So let's look at our unit circle over here, and we know that the tangent has to be negative, and pi over 3, this is pi over 3, pi over 3, the tangent of pi over 3 is positive. So using our reference angle of pi over 3, we know that the tangent of here is negative. So we know our angle 3 right over here. And we know that the arctangent of √3 is pi over 3, and the arctangent of negative √3 is over 3, because the tangent in the fourth quadrant over here is negative, and the angle over here in this quadrant is negative pi over 3. And you might be wondering that the tangent in this quadrant is also negative. So why couldn't the arctangent of negative √3 be in this quadrant? The answer is actually yes, you're indeed. However, the arctangent of a function has restriction. Why? Because the arctangent of function is the inverse of tangent function. Technically, because the tangent function isn't a one-to-one function. In order for the tangent function to have an inverse function, we need to restrict the domain of the tangent function. So after we restrict the domain of the tangent function, we restricted the range of the arctangent. Range of the arctangent function pi over 2 and pi over 2. So the range of the arctangent function is between negative pi over 2 and pi over 2. Range of the arctangent function, and that's or the value of the arctan of angle, or sorry, the value of arctan. So arctan of x could only be between negative pi over 2 and pi over 2. And if our angle is over here, our angle would be pi minus pi over 3, which would be 2 pi over 3, which is larger than pi over 2. So it can't be 2 pi over 3. And our angle couldn't fall in here, because it's just a convention of restricting the domain into like negative pi over 2 and pi over 2. That's the standard. So yeah, here we have our answer, where our arctangent of negative √3 is equals to negative pi over 3. Here then. Perfect is correct. So the solution is correct. Correct. Great job. Solution is correct. Cool. So we have 2 more minutes till the end of our stream. Let's see what the next question is to see if we can finish it. We can finish it. Okay. So our 14th problem over here is asking us to convert 88% into a calc before the percentage sign essentially just means 1 over 100. So in order to convert 88 into a fraction, we just do 88% equals to 88 multiplied by 1 over 100, which is essentially what the percentage sign means. So we would have 88 over 100, and then want to simplify it. The greatest common factor of the numerator and the denominator, in this case, is 4, so we just divide we just divided it for both 88 and 100. So let's 88 divided by 4 is 22. 100 divided by 4 is 25. So 88% in fraction is 25. And over here, nice. Let's look at the sample solution. Yep, they had the same solution. The solution is... Good job! Yay! Now, we're right on time. Perfect! So that is the end of our live stream today. Thank you so much for coming. I hope you enjoyed the math problems. They are the most commonly asked math, they are the most commonly asked math problems on our website, and that's why we're solving it today. So yeah, I hope you enjoyed it, and if you really liked our videos or our live streams, please hit subscribe, and I hope to see you again in the future. Nice!